Hi, we're going to talk about section 10.1 today. 10.1 deals with sequences and series. The definition of a sequence is an infinite sequence, meaning it goes on forever, is a function whose domain is the set of positive integers. Rather than using function notation, our sequences will be using subscript notation. Subscript notation is what you see right here. When you use subscript notation, each term of the sequence is represented by a sub 1 or a sub 2. So the first term would have a subscript of 1, the second term would have a subscript of 2, the third term would have a subscript of 3, and the nth term would have a subscript of n. Sequences whose domains consist only of the first positive n integers are called finite sequences. When we're working with these problems, we are going to plug in values for n based on the directions. So our directions tell us to find the first 4 terms of the sequence, which means I'm going to plug in 1 for n to find the first term. I'm going to plug in 2 for n to find the second term. I'm going to plug in 3 for n to find the third term, and I'm going to plug in 4 for n to find the fourth term. N is right here in my rule, so I only plug it in where I see an n in the rule. And then I evaluate. So negative 1 to the first power is negative 1. Negative 1/2 squared, I said that wrong on the first one. Negative 1/2 to the first power is negative 1/2. Negative 1/2 squared would be negative 1 squared and 2 squared. So in a fraction, you have to square the top and square the bottom. Negative 1/2 cubed would be negative 1/8, because you would cube negative 1 and cube 2. And negative 1 to the 4th power is 1, and 2 to the 4th power is 16. So here are my first 4 terms. You guys can do the work on your calculator, or you can do the work by hand like you see here. It's totally up to you. On the second example, you're going to do the same thing. To find the first 4 terms, you're going to plug in 1 for all your n's. So wherever you see an n in this problem, it's going to get replaced with a 1. I do recommend that you do this on your calculator, and when you plug all this into your calculator, you have to remember to put your numerator and denominator in its own set of parentheses. If you do this right, you should be getting a value of 2 on your calculator. So you're going to have to do this for each term. To find the second term, you plug in 2 for all your n's. Again, when you evaluate this on your calculator, you have to put everything in its own set of parentheses so that you do things using order of operations. And if you do this right, you should get 14/9. Then to find the third term, you're going to plug in 3. So wherever you see an n in your rule, it gets replaced with the number of the term you're finding. And then for the fourth term, you would plug in 4. If you're doing this on your calculator, you would not have to show all of this work that I'm showing. You would just have to give me the final answers. Try it on your calculator to make sure you're plugging in everything correctly. You should get for the third term 28/19, excuse me, and the fourth term 16/11. So 2 for the first term, 14/9 for the second term, 28/19 for the third term, and 16/11 for the fourth term. make sure you're paying attention to your directions. In example 2, all you have to do is find the indicated term. So in this case, we only want the 16th term. So to find the 16th term, we just have to plug in the 16 for all of our n's. And again, you guys will have access to your graphing calculator, so use it. So this is going to be -1 to the 15th power, which will stay -1, because when you raise to an odd power, it stays negative. Even powers become positive. And then times 16 times 15. So it ends up being -240. Why don't you guys pause and go through D? Again, I highly encourage you guys to do this all at once onto your calculator. If you did this correctly, then you should get 37 over 130 for the 13th term. On these next examples, we're going to write the expression for the nth term, which means we're going to write the rule. These can be a little bit harder in this section than the rest of the homework, so just try your best. Eventually, when you have to write rules come test time, you will have formulas to follow when you do that. So if you look at this first problem, you can see that you are increasing by 4 each time to get to the next number. If you add or subtract to get to the next number, that is called an arithmetic sequence. If it's an arithmetic sequence, you have a formula to use to find the rule. You do not have to use the formula. If you know that your pattern increases by 4 each time, then whatever number it increases by will be the coefficient in front of n. So my rule is going to start out 4n. Now I need to understand hang on a second, I'm having some technical difficulties. My rule is going to start out as 4n, but I need to understand that in order for me to get the first term, which is 3, I have to plug in a 1 for n. In order for me to get the second term, which is 7, I have to plug in a 2 for n. In order for me to get the third term, which is 11, I have to plug in a 3 for n. So if I look at what I've done down here, I can see that 4 times 1 is not equal to 3. But if I subtract 1 from that, it will be equal to 3. 4 times 2 is 8. If I subtract 1 from that, it's 7. 4 times 3 minus 1 is 11. So if I would subtract 1 from the 4n, I'm going to get a rule that fits this entire sequence. That's what I'm trying to do. Write the rule for the pattern. This next pattern is a fraction. So I need to write a rule for the top and I need to write a rule from the bottom. If your numerators alternate from positives to negatives, I recommend that you always start by using this rule. Sometimes this rule works, sometimes this rule does not. So again, in order to get this term, I'm going to plug in 1 for n. In order to get this term, I'm going to plug in 2. In order to get this term, I'm going to plug in 3, and in order to get this term, I'm going to plug in 4 for n. So if I'm just looking at the top right now, if I take, for the first term, negative 1, and I raise it to the 1 minus 1 power, that would be negative 1 to the 0 power. Well, anything to the 0 power is 1. And 1 is what I want for my numerator for the first term. If I plug in a 2 for n, negative 1 to the 2 minus 1 is negative 1 to the first power, which is negative 1. And that's the numerator I want for my second term. So this rule does work. Now I need a rule for the bottom. Well, if I look at the bottom, I know that it goes 2, 4, 8, and then 16. If I were to use that 2 and raise it to the nth power, I would get all of my denominators. Because 2 to the first is 2, 2 is the denominator I want for my first term. For my second term, if I took 2 squared, I would get 4. I'm going to skip G, and I'm going to move on to H. If I look at H, all of these have a 1. Whoa, I'm so sorry. Just totally moved on to the wrong thing. So let me get back to what I needed to be at. All of these terms in the pattern have a 1 plus a fraction. So my rule is going to be 1 plus something. Well, if I look at my denominators are the same denominators as I had before. So I'm going to use the same rule as I did in the last example. 2 to the first is 2, 2 to the second is 4, 2 cubed is 8, 2 to the fourth is 16, 2 to the fifth is 32. Now if I compare my denominator and my numerator is 1 less than my denominator. So if I already have a rule for my denominator of 2n, 1 less than that's just going to be minus 1. So there's my rule for this pattern. Now we're going to move to recursion formulas. To define a sequence recursively, that's a key word, you need to be given one or more of the first few terms. All other terms of the sequence are then defined using the previous terms. So whenever you see the word recursive, what that tells you is that you're going to use a previous term to get the other terms in the pattern. So when I look at this example, I can look and see that in the directions it says to write the first 5 terms, not 4, first 5 terms of the sequence defined recursively. Whenever you see the phrase defined recursively in your sorry, I'm focusing on something else right now. In your directions, you are going to see somewhere in your rule a subscript of n minus 1. And I totally blocked that out. So let me just circle it. When you see this subscript, that means it's going to be a recursive formula. So what this means is that to find the second term, because the first term was given, to find the second term, you're going to plug the first term in here. So to find the second term, I'm going to do 1/2 of 32. That's 16. Now to find the third term, I have to use the previous term. So I'm going to do 1/2 of 16. To find the fourth term, I have to use the previous term. So I'm going to do 1/2 of 8. And to find the fifth term, I'm going to use the previous term. So I'm going to do 1/2 of 4. So my answer for the first 5 terms of this sequence will be 32, 16, 8, 4, and 2. If I do this again, I'm going to always plug the previous term into here. So they have to, in a recursive formula, give me at least the first term. So my first term is going to be 14. Then I'm going to take negative 2, because that's what's in my rule, times 14, and that gives me the next term. So that's negative 28. Then I'm going to take negative 2 times negative 28, and that gives me the third term, which is 56. Then I'm going to take negative 2 times 56, and that gives me the fourth term, which is negative 112. Then I'm going to take negative 2 times negative 112, and that gives me the fifth term, which is 224. Sorry, not 225. 224. Okay, our next set of examples deal with factorial notation. Hopefully you've seen factorial notation. Factorial notation is the little exclamation point. In math, it's read as n factorial if n is a positive integer. Factorial notation means that you're going to be multiplying, starting with the number 1, all the way up to the number n. So 5 factorial would be 1 times 2 times 3 times 4 times 5. 6 factorial would be 1 times 2 times 3 times 4 times 5 times 6, and so on. There is one special case with factorial notation, and that's 0 factorial. And 0 factorial is always equal to 1. You do have a factorial button on your calculator. So get your graphing calculator out. Press pause if you need to. 25 factorial is just 1 times 2 times 3 times 4 times 5. These are all times in between here. It's not really showing up. All the way to 23 times 24 times 25. Instead of actually taking 1 times 2 times 3 times 4 times 5 all the way up to 25, you can type in 25 factorial by hitting the number 25, then hitting your math button, arrowing over to probability, and most of you it'll probably be number 4 is your factorial button. So type in 25 factorial and then divide it by 23 factorial, and if you've done this right, it should be I got interrupted on that last example, so I'm going to have to start over. Sorry, I'm starting over with example A, or example K. You guys can type in 25 factorial divided by 23 factorial on your calculator, and you get 600. The factorial button is found by hitting your math button, arrow over to probability, and then you'll see it. You need to understand what factorial does, though. 25 factorial is just 1 times 2 times 3 all the way up to 23 times 24 times 25. 23 factorial is 1 times 2 times 3 all the way up to 23. So the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 23 are all going to cancel. So in the end, to figure out what 25 factorial divided by 23 factorial is, you just have to take 24 times 25. That's where that number comes from. This idea is going to help you when it comes to variables being involved. So if you think about this, the numerator 3n plus 1 factorial is 1 times 2 times 3 times 4 all the way up to 3n plus 1. Well, the term before 3n plus 1 is 3n plus 1 minus 1. The ones cancel. So the term before 3n plus 1 is just 3n. Well, on bottom, we're dividing by 3n factorial, which is 1 times 2 times 3 times 4, all the way to 3n. So the 3n's are going to cancel. The 4, 3's, 2's, and 1's cancel. So when you actually see what's left, it's just 3n plus 1. So you guys try example 6. Example 6 you can do on your calculator. We're writing the first 5 terms of the sequence. So to find the first term, you're going to do 1 factorial divided by 1. To find the second term, it's going to be 2 factorial divided by 3. To find the third term, it's 3 factorial divided by 3. Fourth term will be 4 factorial divided by 4. And fifth term will be 5 factorial divided by 5. Plugging all of this into your calculator gives you final answers of 1 for the first term, 1 for the second term, 2 for the third term, 6 for the fourth term, and 24 for the fifth term. Last but not least, we have summation notation. Summation notation is represented with what you see on your screen, on your paper. When you look at this, I is called the index of summation. N, which is above the sigma, is called the upper limit of summation. The number 1 is called the lower limit of summation. And the big E symbol is called a sigma. It's a Greek letter. We're going to use summation notation to help us find the sum. So instead of listing the first 5 numbers or the first 4 numbers or the first 3 numbers, we're going to find those numbers and then add them together. Whatever you see on the bottom is the lower limit, but that's the first number that you plug in for J. So 1 over 3 squared minus 3 is the first term. Since the upper limit's 5, that means that we have to plug in the numbers 3, 4, and 5. So the upper limit tells you what number to stop at. But instead of putting a comma, we're going to put a plus sign. So we're going to plug in 4, then we're going to plug in 5. When we do this math, we actually get this to equal 1/6, this to equal 1 over 13, and this to equal 1 over 22. When I add those up on my calculator, the final answer for the sum of those 3 numbers will be 124 over 429. In this example, what you have to understand is that the rule for each term is 5. So you are told with the lower limit to start by finding the first term. The upper limit tells you that you need to add the first 5 terms. Well, your index of summation is K. There's no K in the rule. So that means the first term is 5, the second term is 5, the third term is 5, the fourth term is 5, and the fifth term is 5. So when you add all of those together, you get the summation to be 25. In the last example, you're going to start by plugging in, a technical error again. Let me get back to where I need to. Oh my goodness. In this next example, I need to plug in 0 because that's my lower limit for J. Then I need to plug in 1. Then I need to plug in 2. Then I need to plug in 3. And last, I have to plug in 4. I can do this math on my calculator. I can do this math just by hand. Anything to the 0 power is 1. Negative 2 to the first power is negative 2. Negative 2 squared is 4. Negative 2 cubed is negative 8. And negative 2 to the fourth power is 16. When I add those all together, I get 11. In these last few examples, we are going to Express the sum using summation notation. So summation notation is where we have the sigma. They tell us in our directions to use I as our index and use 1 as your lower limit. So in this case, since 1 is equal to I, I'm going to replace 1 with I to write my rule. So I'm going to say that my rule, which always comes after the summation, is I to the 4th power. So if I plug in 1 for I get 1 to the 4th power. If I plug in 2 for I get 2 to the 4th power. If I plug in 3 for I get 3 to the 4th power. Those are the first 3 terms in the summation given at the beginning of this example, which means my upper limit needs to be 12. So this is my final answer for my summation. And this is the rule. On example R, I use I as my index, 1 as my lower limit. So again, 1 is equal to I. So when I write my rule, wherever I see a 1, I'm going to replace it with an I. So my numerator, the rule is I. If I is equal to 1 and my denominator is 3, 1 plus 2, or I plus 2, would give me 3. So now I need to see if this rule right here fits the rest of my pattern. So if I plug in 2 for I, is 2 plus 2 4? Yep, and that's my second one. If I plug in 3 for I, is 3 plus 2 5? Yep, and that's my third term. So now I need to look here to find my upper limit. My upper limit has to be 16 so that I get this term for my last term in my pattern. So here is my final answer for that summation. In this last example, the directions change a little bit. We are still going to write our answer using summation notation, but this time it says to use K as the index, and your lower limit could be anything you want. So if you look at this, all of these values are increasing by 2. So if I multiply 2 times K, what would K have to be to give me 6? It'd have to be 3. What would K have to be to give me 32? It'd have to be 16. There's my rule. If you let K be something besides 3, you're not going to get this same answer. So the rules, these are your rules, change, and your lower limit and your upper limit change depending on what you pick. In the last example, again I have to use K as my index. If you look at each one of these terms, they all have an A in it. Most of them have an R in it. So I'm going to ask myself, what can I raise R to make it disappear? And the answer is 0. So if I would make this a 0 power, R to the 0 power is 1, which would just leave me with A, which is my first term. So if I let K be my power, and K is 0, that's how I get the first term. If K is 1, I'd get the second term. If K is 2, I'd get the third term. So if K is 14, I'd get the last term. There's my answer. Hopefully this makes sense. If you need to come in for some extra help, go for it. And make sure you guys have final exam review pages done and ready, along with your bookwork ready.